Hello, General Chemistry crew. We are talking about, in this video, still this notion of entropy, but we're going to be taking it, a little bit further today, of course. And so what we know so far is really this idea of the second law of thermodynamics. And basically what the second law said was that for, a process to be spontaneous, the change in entropy of the universe must be positive. And that's coming back to this expression in terms of relating the entropy of the universe to the system and the surroundings. So that's really the distilled down version for, a spontaneous process. Our delta S of the universe needs to be positive. So if our delta S is positive of that universe, we have a spontaneous process. If it's negative, that will be non-spontaneous. So that's the logic that we're looking at today in this lecture, and going just a little bit further in terms of this expression and being able to go to the next level. This works very well for phase change or phase changes. And we discussed that in a prior lecture looking at, water or ice and its ability to freeze or melt, respectively. However, this is more problematic when looking at reactions. It's gets a little bit more complicated. The delta S of the surroundings is complicated due to the number of probabilities that can occur. The system is easy to relate since, the chemist is in control. When the chemist sets up the reaction, the chemist knows the temperatures and atmosphere and etc. The chemist can control the actual system, but not so much with the surroundings. So that becomes the problem. And so it would basically be nice if we could look at reaction or reactions and their possible spontaneous nature by being just in terms, or by being just in terms of the actual system or reaction. So that's where we're going in this lecture, is now to, be able to still look at having some predictability of whether a process is spontaneous or not spontaneous, whether the reaction will go or it won't go, but have it totally within the actual system, the system environment. And the system environment is the one that we can actually create as chemists. And that's why we have this notion now of the Gibbs free energy. Gibbs free energy is given to us as delta G, and that is in terms of kilojoules per mole. Remember, we have standard state still here, as far as our pressure of 1 atmosphere, concentration of 1 molar, temperature of 298 Kelvin. So all that is still there. So what is the Gibbs free energy? Well, the Gibbs free energy is, basically an approximation of the entropy of the universe in sole terms of the reaction. So there is kind of a sign issue. The delta S of the universe is basically the same as saying the delta G of the reaction. But there is an opposite sign issue. So if our delta S is positive for the universe, then our delta G would be negative. So we have that opposite sign relationship between the two. We could say, the exact opposite of that, right? That if we had a negative delta S of the universe, that would correspond to a positive delta G for the reaction. So here we have our negative delta S of the universe, and so that is equal to something now that is non-spontaneous. And we have our delta G of the reaction is positive, and that is also something that is non-spontaneous. So the delta G really gives us a way to just kind of look at the reaction and the materials that we're starting with, the materials that we're producing in the reaction, and then be able to really approximate whether this is something that is a spontaneous process or not a spontaneous process based on those signs. So now that we have an idea of how signs of delta G relate to spontaneity or non-spontaneity, from this relationship of the universe, we can now start looking at, the Gibbs free energy equation. And the Gibbs free energy equation, we've had this up in the past, but we can do it obviously again. Looks like this, right? Where we still have, this notion of standard state. Right? We see that with these, superscript zeros. And remember that this talks about, 1 molar solutions, 1 atmosphere, 298 Kelvin. We tend to go to tables for these types of values. And remember, our delta G here likes to be in terms of kilojoules per mole, as well as our delta H. Our entropy is in joules per mole Kelvin, which then means our temperature must be in Kelvin. So we have our Gibbs, we have our enthalpy, we have our temperature, and we have our entropy. So those are the different components to the Gibbs free energy expression, and really these are all in terms of the system, right? In terms of the actual reaction, as far as that's concerned. So there is our Gibbs free energy, and what I'd like to do is kind of blow it apart a little bit and just start to look at it qualitatively as far as signs and driving forces. So let's consider this idea of driving forces for spontaneous reactions. And remember, that means that we want to have, a negative delta G, for a spontaneous process. So if we go to the equation above, there's two features that are driving forces. One would be enthalpy, one would be entropy. A negative delta H of reaction is an exothermic reaction and is a driving force for spontaneity or for spontaneous reactions. So that's one type of driving force is our enthalpy. If we have a negative enthalpy, well then that leads itself to a negative delta G according to the expression for Gibbs free energy. And so that would be a driving force. We could also say, the opposite scenario is that, a positive delta H of reaction is, an endothermic reaction and is not a driving force for spontaneous reactions. So there's our enthalpy component in terms of, these signs, right? As far as, okay, if I have a negative sign for my enthalpy, well, then that's the good feature, and so that lends itself to spontaneity or to spontaneous processes, reactions, while a positive delta H is the opposite and doesn't lend itself to the possibility of a spontaneous process. We can do something very similar with our idea of delta S, or this idea of entropy. If we look at that, a positive delta S of reaction, or entropy of reaction, is a reaction that is increasing in entropy, and this is a driving force for spontaneous reactions. So remember that with entropic ideas is that we're always looking for more entropy or increase in entropy for spontaneity. And so that's why we have the positive sign for the delta S now attributing to that cause for a spontaneous reaction. If we have a negative delta S of reaction, this means that this is a reaction that is decreasing in entropy and is not a driving force for spontaneous reactions. And so that's what we have with our entropy. So that's just kind of looking at signs and what we've talked about in the past as far as, whether something is, kind of a driving force or not given that sign. Exothermic reactions in terms of delta H are negative. That's a driving force because they give off heat and they can continue that process, supplying enough activation energy to keep the process going. Entropically, we want to have an increase in entropy or a positive value. So we have, these different signs to describe, different aspects of the reaction. One aspect is enthalpy of the reaction. We would like that to be exothermic or negative. The other part to this equation or to these types of processes would be entropy. And we want an increase in entropy or a positive entropy for a spontaneous process. So let's go back to, and I'll write it again here, our expression for Gibbs. And let's expand on it a little bit more in terms of the different components that are there and get a little bit more specific, with delta H, delta S, the signs that we just talked about, but now let's bring them together and start to relate them to one another and start to recognize spontaneous processes because of driving forces, or non-spontaneous process because of the lack of driving forces. But we'll find there's a third category in there as well, which is basically temperature-dependent processes. So if we break it down, we could look at, this in three different, kind of components. There is our delta G of the reaction. There is our delta H of the reaction. And then there's also T delta S of the reaction. So those are, different components that we can have in terms of sign, in terms of value. So what we want to start doing is just kind of putting in different signs that you could possibly have. So let's say we have a positive delta H. And we could say that this is not a driving force, right? We talked about that just a little bit ago, right? This is an endothermic reaction. Let's say that we have then also a positive entropy of the reaction. This is a driving force. And the reason for that is if we look at T delta S, is that T delta S is now negative because of the sign change. Or we have that minus T delta S. So if now we plug that into the expression, we have like a negative portion and a positive portion. And that means for delta G is that this is temperature dependent. As temperature increases, so does the spontaneous nature of the reaction, right? We're trying to weigh out two things here. In this case, we have not a driving force, which is the delta H. We have a driving force, which is delta S. And because of that idea of one contributing to spontaneity and one not contributing to spontaneity, that's where temperature is going to come into play. Eventually, our temperature will be so large that the T delta S portion, or that negative portion of the equation in this particular example, now will be greater in magnitude than the positive portion of the equation, or the delta H. And so that's why this is a temperature-dependent process. And so we're looking at temperature increase leads to a spontaneous process. Now let's just change, one of the signs. Let's say that delta H is now negative. This is a driving force. And if we have a positive entropy, again, this is a driving force. because T delta S is now negative because of the sign change. So here we find two things that are driving forces, the delta H and the delta S. And so what does that mean for delta G? That means our delta G of the reaction is always negative, and this reaction is then always spontaneous. So if we're looking at this color coding, we can see kind of blue and red, or blue and blue, right? So if we see blue and red, that's what we're going to find is always a temperature-driven process. We see blue and blue here, then that means that's always a spontaneous process. It doesn't matter what the temperature is, it's always going to lead to a spontaneous reaction. So we change the delta H sign. Now let's keep the delta H sign consistent, and let's look at changing the sign of delta S. So if our delta H is still negative, this is again a driving force. However, if we have a negative delta S of the reaction, this is not a driving force. Our T delta S of the reaction is now positive because of the sign change. So again, we find now we have one that's beneficial to spontaneity, delta H, and one that is not leading to spontaneity, which is delta S. And so this is again a temperature dependent process. So as temperature decreases, now the spontaneous nature of the reaction increases. Here, now that we find that one is a driving force and one is not, we want to try to minimize the feature that is not a driving force. And so that's the delta S side of things. So if I decrease my temperature, I'm decreasing the magnitude of T delta S. And eventually, the negative delta H portion of the equation will now be much larger in magnitude. And so now we end up with a spontaneous process. So we can have reactions that are temperature dependent, meaning that if I increase temperature, that increases spontaneity. And that was the first example we did in this table. Or we can have another temperature dependent process, which is if we decrease temperature, it lends itself to spontaneity. That temperature dependence is really driven by which one is not the driving force, and we're trying to minimize that aspect of which one is not helping the spontaneity of the process. And the last example here, now we're going to change delta H back. Delta H will put as a positive sign now. And so that's going back to the first part of the table where this is, not a driving force because of its endothermic nature. And then if we keep our entropy the same, right, we find the same, ideas above, right? This is not a driving force, and again, because T delta S of the reaction is now positive, because of the sign change. And so this leads to our delta G is now always, doesn't matter what the temperature is always positive. And this reaction is never spontaneous. So that is a table to try to just put together the idea of sine of delta H, sine of delta S, and how that has an impact on the sine of delta G. If our delta H and delta S are both driving forces, namely a negative delta H, a positive delta S, that means we always have a spontaneous reaction. However, we flip that, we have a positive delta H, not a driving force, negative delta S, also not a driving force. That means the reaction is never spontaneous. Doesn't happen. And then we can have where one of those two, the delta H or delta S, is a driving force. And when we only have one as a driving force, that's when we lead to this idea of temperature dependence. So if both are driving forces, always spontaneous. If neither are driving forces, it's never spontaneous. And if one is a driving force, now we have a temperature-driven process. Sometimes that's increasing temperature, sometimes that's decreasing temperature. But again, that's just going back to trying to minimize the force that's not driving the process, trying to minimize that magnitude. So that is our kind of introduction to the idea of delta G, to the Gibbs free energy expression, and to this idea of spontaneity and non-spontaneity, and how that is impacted by our signs of delta H and of delta S. In a subsequent lecture here, next, we're going to get into some example calculations of delta G, putting this all together with the Gibbs free energy expression, as well as going on to a couple other versions of Gibbs equations that we can use in thermodynamics. Look for that next.